All right, now that we know how to use the Biot-Savart law to calculate or estimate the magnetic field due to a current carrying wire, we are going to introduce what's known as Ampere's law. And Ampere's law, analogous to Gauss's law, allows us to determine the magnetic field of a current distribution solely based on the current that's enclosed in what we call Amperian loops. So very similar to when we did Gaussian surfaces and said that the electric flux is equal to the charge enclosed over epsilon naught. And then given symmetries like spherical or cylindrical symmetry, we could solve for the magnitude of an electric field. So much in the same way, that's how we're going to use Ampere's law. So the statement of Ampere's law is sort of simple right here. So if you draw any closed loop in your problem, and you go around that loop and evaluate the magnetic field dotted into the path length, so around the path, if you do that closed integral, that closed path integral, then that's got to be equal to mu naught times the current, and I've made this little arrow here, the current enclosed inside the loop that you've drawn. And so the two pictures below kind of demonstrate this. So I've got on the left-hand side, I've got a current carrying wire with current coming out of the page, and we've drawn this path M around the wire, and then on the right-hand side we've drawn the path N, and those are just arbitrary paths, but you'll notice that the path on the left, if inside that closed path there's a current carrying wire, current I, and on the right-hand side there's no current inside. And so the awesome thing about Ampere's law is that immediately you can say the following. You can say immediately that on the left-hand side, that path integral b dot dl over the path m, that's got to be equal to mu naught I. And on the right-hand side, that path integral b dot dl over the path n has to be equal to 0. And the reason you can say that immediately about those two examples is on the left, there is current inside the path that you're going around. And on the right-hand side, there is no current inside that path, inside the loop. And so Ampere's law allows you to immediately determine what that path integral has to be equal to. Now, just like with Gauss's law, Ampere's law is always valid. It's always true, but it's not always useful. Just like with Gauss's law, we need to leverage paths that take advantage of symmetries in the problem. And when we do that, just like with Gauss's law, we'll be able to bring out that b in the path integral. If we choose our path correctly so that b is constant, we'll be able to bring that out of the integral and solve for the magnitude of the b field. So let's look at an example where we can do this. All right, so the example that we're going to look at, we want to determine the magnetic field due to a long, straight, current-carrying wire. And we already know the expression for what the magnetic field strength is due to a long, straight, current-carrying wire because we derived that expression using Biot-Savart previously. But what we're going to go through here is how to determine that using Ampere's law, and what we're going to notice is that it's much simpler, much more straightforward to use Ampere's law. Just like in electrostatics, if you could use Gauss's law to determine the electric field, it was always much simpler and more straightforward. All right, so I've got my my current carrying wire over here, and I've got current coming out of the page, and I've drawn just a circular path centered on the wire, and that the radius of that circular path is little r. So we're just going to start with Ampere's law. So just write it out. And in this problem, current enclosed, I enclosed is just I, the current in the wire. So the question is whether or not we can do anything with this left-hand side to try to figure out what the magnetic field strength is. So here are a few things that we should appreciate. First off, the B field, the vector, must be perpendicular to both I and R. Here I've just drawn R as a length, but there's a vector R, right, that you can associate with that length. So the magnetic field must be perpendicular to both of those quantities. So the current's coming out of the page, and R is sort of that distance or that direction either towards the center of the circle or away from the center of the circle. So that means that B has to be pointing tangent to the circle. The other thing that we want to appreciate is that B only depends on R. So the magnitude of B, no matter where we are on the circle, right? So no matter where we are on this circle, the magnitude of the B field is going to be the same value. And so when we realize those things, then this expression can turn into this expression because the magnetic field is constant over that path. And so I'm just going to bring it out of the integral. Well, now we're just integrating dl over the path of a circle, which is just 2 pi r. And then we just move to the other side, and we end up with what we were expecting to get, because we came up with this from BO sub r. But we get that the magnetic field, due to a long straight current carrying wire, is mu naught I over 2 pi r, and the direction we can get from the right-hand rule. So your thumb pointing in the direction of the current, and then curl your fingers around the wire, and so in this case we would have a counterclockwise magnetic field. So the direction of the magnetic field changes as we move around that path. So let's look at a second example here of how to use Ampere's law. Here we have a long straight wire that has radius A, and the current that's flowing through the wire is distributed uniformly across the cross section of the wire. And we want to find the magnetic field inside and outside of the wire. So looking at sort of picture B here in the figure, the current that's flowing through the wire is uniformly distributed over the surface, over the cross section there. And so we need to think about, if we sketch our Amperian loop, like drawn there in the yellow, how much current is actually enclosed in that loop, and how does that change as we draw larger or smaller loops. And so, so the approach here is exactly like what we would use in Gauss's law. How the current enclosed changes as the Amperian loop changes depends on the size of the loop. And so, in general, we can always start our Ampere's law problems like this. And remember, that's exactly how we would start our Gauss's law problems as well. And so we start with this expression, and then the question really is, what's the current enclosed? And so I'm going to first look at when R is less than A, so inside the wire. So I enclosed inside the wire is equal to this expression, J times 4 pi r squared. Well, first off, what is J? Remember, J is the current density. That is the current per unit area. And so in this problem, we're told that the current is uniformly distributed, so that means the current density is just I naught, the value that they give in the problem, divided by the full cross-sectional area, 4 pi a squared. And so I enclosed then is the current density J multiplied by how much of the wire you're actually enclosing with your Amperian loop. And so I enclosed is just going to be I naught multiplied by the ratio of r squared and a squared. And so you can check to see if this makes sense, because if you set r equal to 0, you're going to get no current enclosed. Well, that makes sense. You've got no loop. And if you let r go all the way to a, go to the edge of the wire, then the current enclosed is going to be I naught, and that's going to be all of the current. So that makes sense. So that means for our analysis, we've got to evaluate b dot dl over this path integral. Well, that's just exactly what we've been doing in the previous problem. B times, and then the circumference of the circle, 2 pi r, and that equals mu naught, and instead of I enclosed, I've substituted in what I solved for, I naught r squared over a squared, and then I just solve for b. And so this is the expression for the B field, the magnitude of the B field inside the wire as you're moving out to the edge with radius A. Now, the next question is, well, what about outside of the wire? Well, again, you start at the exact same spot. And now, I enclosed, when you're outside the wire, I enclosed is just I naught. And so that means when you go to do Ampere's law, you immediately can solve and get the expected expression that the magnetic field outside is mu naught I naught over 2 pi r. And again, these are just the magnitudes, right? If you want the directions, then you've got to think about the right-hand rule. And what I've included over here on the right is just a little plot of what the magnetic field looks like in these two scenarios. So as you're moving from r equals 0 out to a, the magnetic field is increasing in strength until you get to the edge of the wire, and then at that point, the magnetic field drops off like 1 over r. All right, so those are two examples of leveraging Ampere's law to solve for the magnetic field. And again, in these cases, we had cylindrical symmetry, so we could immediately pull B out of that path integral, and we could solve for the magnitude of the B field. So anytime you can leverage a symmetry like that, you can immediately use Ampere's law and avoid using the Biot-Savart sort of brute force integral to figure out the magnetic field.